today will be the third lecture, and I will use the first half will be with slides, and the second half will be, after the break, will be on the board. And the first half of the first quarter or slightly more, will be a short revision, or I will quickly go over the slides from the first talk, which are relevant for this talk. Not the second talk. The second talk was on a different scope. Okay, so the topic for today would be, I'll come back to the concept of local weak convergence and the beta prediction. So that will be what we will do today. So I want to remind you about the Ising model on a general graph. And we will have now a sequence of graphs whose size is going to be n, the number of vertices, and there are going to be a certain set of edges. The Ising variables are plus or minus 1. They just shifted from sigma to x everywhere. And this is the Ising measure with e to the beta sum of the xi is j and extramagnetic field b. And we will distinguish between beta being negative being the antiferromagnetic and beta being positive being the ferromagnetic. In the ferromagnetic case, you are trying to make all the xi the same sign. In the antiferromagnetic, you are trying to make all of them to be opposite sign to each other, but this is pretty impossible once you have loops, so the situation is more difficult. Now, I will, without loss of generality, make b greater or equal to 0. The reason being, you can see that changing the sign of beta or b and changing the signs of all the x's, you come up exactly to the same solution. So, whatever the answer will be, whatever result I will get for b, which is no negative, you can get the same stuff for b, which is negative, by simply remembering to shift all the signs in whatever conclusion I get, or whatever derivation I get. A generalization of the Ising case is the Potts model, which I will discuss also. In the Potts model, what you have now, you have q different species instead of 2. The case q equal 2 corresponds to Ising. Now, what you're doing, you are not taking, you are not separating the product, the operation xi xj over plus minus 1 is the same, exactly the same, up to constant as taking an indicator of xi equal to xj. Because if you take two numbers which are plus and minus 1 and you multiply them, you either get 1 or minus 1 depending on whether they are the same or not. But with q numbers, you cannot do that, so you replace it with this indicator. So what this indicator is doing is if beta is positive, the ferromagnetic, it tries to make the states all of the same color, the same type. And if it is negative, it is trying to make them opposite. And like in the case of Ising, you can add a magnetic field by giving a distinction to one particular number 1, right? But of course, I can do a permutation, change the 1 to 2 and so on. It will just be the same as again, permuting the different q's so that one is distinguished. You just like to call the one to be the distinguished one. And as I mentioned, taking the case q equal to 2, up to some changes of constants, it's the same as the Ising measure. The Ising corresponds to Potts of 2. And the third model that will appear here, but much less so, will be the hardcore model. And the hardcore model has now the spins takes the value 0 and 1, and you have a constraint. The constraint is preventing two neighboring sides to both be 1. Right? If both of them are 1, you get here a 0 that kills the whole measure. This means that the set of states which are 1 form an independent set. There are no edges between 2 which are 1. And then you have this analog of magnetic field, which is called e to the b, is usually called lambda, the fugacity, and it gives a different weight according to the size of the independent set. We mentioned that if you take b equal to 0, you count the independent sets of the graph, and if you take if you look at the limit as b goes to infinity, you will get the hardcore ground state energy. So these are the three models we will look at. And more generally, we will use this framework whenever possible. So we have a product of terms involving edges and a product of terms involving just a vertex. And let me write you explicitly on the form what will be the special cases that correspond to our three examples. It's not necessary to have just a picture. So I will write here that the factor model. So let me write you the formula for the partition function, this quantity. This will be of interest to us. And the partition function Zn will be the sum of all possible x. The main product model comes from the fact that it's a sum of products. Partition function is a sum of products. And then we took the case of teasing. Just show you how they fit all together. Case of course. Three special cases, and we will be interested in this lecture in the limit, if it exists, 1 over n. That will be of interest to us in this lecture, just to calculate this limit in many cases. So let's see. We have a graph sequence. Here is the factor model. I just wrote you the record exactly the content of the slide. And we are interested in finding the asymptotic free energy density, which is the 1 over n log of this here. We would expect Zn in general to grow or exponentially. Right? Because even if these are indicators, there are in general x to the power n, the states that are n vertices here, there are in general x to the power n, size of x to the power n such objects, and we want to know how many of them are satisfying the constraint. Or if it's weighted, then there will be some numbers. And in general, while I did not write it, this is a function of certain parameters. So this is also a function. I somehow embedded these parameters, but the parameters are appearing here, as you can see, right? So there are parameters, which are usually you keep the b and beta for this function, and b for that function. In principle, it may be more than one parameter. And the fact that you have real parameters will allow us, and that's not something we will use, also to differentiate with respect to this parameters, which we will do also. Okay, what kind of graphs we are taking? I remind you, we typically may take the Erdo-Shreni graph. Most of this lecture, if anything, I will take the random regular graph, and I can take more general graphs. These are two examples of graphs which are sparse graphs, so degree D, here I change from gamma in the first lecture to D. The degree D is order of 1. The size n will go to infinity. With the random, in the Erdo-Shreni graph, you only restrict the number of edges, which is proportional to the number of vertices. The ratio between them is an average degree. Or alternatively, you can take an IID if you prefer. This gives you way more independence. This gives you more regularity, which we will take advantage of later. But do here, we take n vertices, but we insist that the degree of the vertices, then I will represent in the future slides the neighborhood of I, or who, and the size is just a number of neighbors. This is the same degree. We want the degree of each one to be exactly d. We choose it such that n times d will be even. So there is a way to do such a graph. There are actually exponentially many such graphs, and we choose one of them uniformly. And then remind you this picture that says at the end of the day that if what we do, we take that the graphs we are interested in are locally tree-like. What does it mean? It means what I just did here before, that if I choose a point at random, I have a large graph, I choose a point at random, maybe this, maybe that, some point. Then for most of the points, if I start evolving, looking at the neighborhood, until as long as the neighborhood size depth is fixed and the graph size grows, I will see a tree. And not only that, but the law of the tree will be kind of a stable limiting law of the tree. Okay? So that's what happens here. In the regular case, here is a tree. In the regular case, a tree can only be the regular tree, because by choice, every vertex has exactly degree d. So if as long as there's no loops, I see exactly one tree, which makes life much simpler. In any other model, I will get a very random tree. So I will have all formulas will involve some expectation or some averaging, or depending on where you are on this limiting tree, which will make things more complicated. So the point is that the d-regular graph converges locally to the d-regular tree, and we also saw that the Erdos-Renyi graph will converge locally to the Galton-Watson tree, and here is a notion of what local reconvergence means for us. What we do, we are saying that we converge locally to some, this is the case of some tree, if we choose uniformly at random a vertex, and we fix t and take n to infinity, we look at the ball, all the vertices of distance t from our chosen random vertex I, then the law of this ball will converge as n goes to infinity to the locus tree. So first of all, the ball of fixed radius will never have a loop, or its probability going to 0 will have a loop, and secondly, the tree is a finite graph. The tree, the finite tree that we see, will come with the same distribution that we expect to come from our tree model. That means that there are going to be consistency here. And secondly, we will say that Gn is uniformly sparse if not only is the average degree constant, which is necessary somehow to get from here at the end a finite tree, but we also want it to be uniformly tethered, which is an extra condition, which helps us. And there is a theory of what the limits can be in Aldous and Lyons 2007, following the definition of local reconvergence from Benjamin and Schramm 2008. And I will refer to this paper a lot, this survey paper with Andrea, which is this is definition 2.1 there. Okay, so some examples. We went over these 3 examples. The random regular tree goes to a regular random regular graph goes to a regular tree. The Erdos-Renyi graph will go to a Poisson tree, a Galton-Watson tree with Poisson degree distribution, and a more general graph of fixed degree distribution will also go if it's uniformly constructed. So you have the degree is coming according to certain rule. So there is a certain rule how to choose a degree. Once you choose a degree, you have all the half edges coming from all the vertices, and you connect them together randomly. What you will get will be a graph, or a limiting graph will be the limiting convergence will be some tree, and this tree will have an offspring distribution that is related to the one you started with, and these results are actually proved in this in detail in this survey paper as proposition 2.5 and 2.6, but they are really kind of redoing things that are known to people in graph theory. So in principle, if you look at the book of Johnson et al., or even the book of Balabash, you will find all the ingredients to these proofs. If you will not find them explicitly written there, you will not find them explicitly written there, but you will find enough ingredients, but we just wrote it on our own. And as I mentioned, the motivation is that natural graph ensembles will fit this scheme. Also, natural randomized computational problems are also described by locally tree-like constraint structure. In lecture 1, we looked at the hardcore, Q-coloring, also K-sat. All the problems will naturally fit this scheme because naturally you would like the number of constraints to be fixed per vertex, otherwise you will not have a solution. Why do we like trees? We like trees because they are amenable to exact analysis. We can write maybe recursive equations. Physicists predict many exact asymptotic results for the setting Gn goes to P. This notation will indicate local reconvergence, where I define it, based on comparison between the models of Gn and of P. So you take your factor model, you can in principle replace the En here by a tree. It's not completely accurate what to do because the tree typically is infinite, so we need to be careful how we do it, but if you can imagine maybe taking a finite tree and writing a model of this type, measure of this type, and a model of this type, and so on. So that's the principle here, and there is a particular prediction which we talked about, the beta replica symmetry prediction for phi of graph Gn goes to P. It says that phi is given by phi bizarre, some explicit form, which depend only on the limiting tree. More or less, it consists of two statements. Statement number 1, if Gn goes to phi locally, then somehow this limit that we are after does not depend on the particular sequence of graphs, but depends only on the limiting tree. Of course, it depends on this function. It will be different for different functions. And maybe the beta prediction holds for certain functions and fails for some other function. That's possible. But it says something, and it also says actually what the formula will be. It gives a recipe how to calculate the formula. So it's a big thing in the sense that it gives you a lot of information. And it also comes from a more general principle about the measure. Let's see if we just here we just looked at the normalizing constant, but in principle I can look at the whole measure of this object and ask questions about how this object looks like. So here is the business with the probability measures, which I mentioned before, the mean field equations. This is our guideline philosophy, but what we are after in this lecture is only this quantity. We are only going to do this kind of calculation, but we are after essentially this kind of prediction. Because this calculation usually comes because this prediction is correct. So once you can do that, you can do that also. Okay, so what is the prediction here? The prediction is as follows. You say, look, what will happen, suppose I remove one edge. I remove one edge of my graph. If the graph was a tree, once I remove one edge, I disconnected the graph into pieces. So if I have a tree, and there was an edge here connecting I and J. So once I cross the edge, well, obviously they are no longer connected because it is a tree. So this is if Gn. But if this is the case, then I can think of calculating the effect. What do I want? I to J. I can calculate the effect of this one on that one. So what I can do, I can write my Gibbs measure. My Gibbs measure involves only edges and variables. So once this is disconnected, all the vertices here and all the vertices here, they will have completely independent, they will have a product measure. This will be one measure, this will be another measure. There is not going to be any factor anymore in En except this one connecting these two sides. So as far as this side is concerned, I can make the calculation, and all that matters is the value of xi. I can take the calculation, the whole sum, all the probability, all the configuration on this side, which end up with xi here, and send it to this guy. Normalize and send it to this. This is mu I goes to jxi. It says as far as this part is concerned, if I disconnect this thing, so I calculate, so if I disconnect this thing, so as far as calculating the whole sum over all this, and rearrange, normalizing, the measure up to here is, as far as I'm concerned, only matter xi. It's very similar to Markov, except it's not ordered sequential. So it's just this only one variable, Here is all the information about the left side as far as the right side of the tree is concerned. But and if we want to update it, what we can think of is going to this place and disconnecting all the children. This guy has only finitely many children, which are connected. But it's already a tree all the way down. So I can go over the 3 children here. And 1, 2, 3. And I can send messages in exactly the same manner, telling the I guy what comes from this tree, what comes from this tree, and what comes from this tree. And if I combine these 3 pieces of information, then I can get an update for this piece of information that I'm supposed to send to this guy. And I can keep doing it. That's the principle. This is what I can do on tree. That's what I mentioned. Trees are amenable to the Gaussian equations. Here are the equations for you. If you take all the messages, you need to multiply by the terms of the relevant edges. You need to sum over all the possible configurations for XL. And you need to take the product over the 3 terms that I have here. Add the local quantity, normalize, and that's what you say. So if you want to have you have a psi here, you have a psi here, you have a psi here, you have a psi bar. And you have messages H, mu, and then you have a mu. I did not write what the existence of this. So this guy summarizes. This guy summarizes this tree. This guy summarizes this tree. This is server summarizes this tree. That's different. You take the effect of these trees, multiply by this thing, sum it all up, and this factor, that's you need to summarize it. It's a little bit of algebra. This it's exactly 33, and it approximates the marginals of mu by measures of trees. I can do more than that. This is a 1 level. Right here, I just did 1 level propagation. I can think of a more general thing where I try to look at the log of 2 of them together, or more generally, the whole red part together. And I can say, oh, if I have a collection like this, which is a tree, and it has a piece here, which are outer vertices, and a piece here, which is inner vertex, I can think of a general principle. I will look at the measure, the right measure I have with the products in these terms, but I will only use it inside the block. So I'm using exactly the Gibbs measure, exactly this collection which I have here, exactly this factor model, but on a much smaller graph. And what do I do with the outside model, where there are maybe possibly loops? I will code it in terms of messages, which represent everything coming from the outside world. There is approximation that I'm not going to take even complicated probability distribution over all of them together. I will replace it with a product. The main point is that I'm suspecting that this is very unusual, and actually all my loops are supposed to be far away. And if they're far away, maybe it doesn't matter, and maybe I can treat it still as if the information coming to the different things is a product. Now this guy is my approximation. It is not exactly the same as a measure, because in the real measure, I have short loops, which may or even long loop, which may make an effect. The meta prediction is just to ignore this. Okay. So this, I did also this slide in the first lecture. Now, of course, what is missing is what to put here. We have a degree of freedom. We are going to put the approximation which is best. So we need to find the best approximation. And once we do that, we also get a principle of the prediction for phi. Right? Remember, I'm trying to calculate the phi, and the prediction says the following: suppose it is a tree. If it is a tree, maybe if GM converges to a tree, what I can do, I can look for a collection of predictions. This is my possible prediction. This quantity is exactly the Gibbs contribution, but in a small neighborhood. Right? So it's this complicated formula with products, but now done on a smaller set. not on the whole graph, but on a much more manageable set view. And then I need to multiply by the product of the messages coming on the boundaries. And if x, for example, if it's an easy model, then I need to choose a probability measure of plus minus 1. If it is a COTS model, I need to choose a probability measure of 1 to q. If it's a hardcore, I need to choose a probability measure of 0, 1. So I need to choose a probability measure on a relatively small space, take a product, add it to these quantities, and of course normalize. This is this wiggle, meaning I always normalize things to get a partition function. Now, what I'm free to choose? I'm free to choose this h star. Every h star that I choose will give me not only a measure, but in principle, after some operations, I can get a prediction for this quantity, assuming that I've just replaced my real probability measure with this quantity. And once I do that, I will get an explicit formula phi of nu star, and now I need to choose a nu star. So nu star is one of these things. Now I have a restriction, and the restriction I have is a self-consistency restriction, meaning this in principle should work for every u. So I can take a big u, let's say a size 3 neighborhood, and collapse to a size 2 neighborhood, and collapse to a size 1 neighborhood. And if I do that, I will get that there is a certain fixed point equation, some non-linear equation that this h star has to satisfy, and I should only look at these fixed points. Maybe there are only few of them, so instead of working on an infinite connection, here I already somehow restricted from all possible probability measures on a big space mu n, x to the n, to only probability measures on the space x. But I want to further restrict it by making the restriction that they satisfy this consistency condition. Maybe I will only restrict it now to 2 or 3 possible solutions. So I want to get as little as possible. If I end up with even 1, I can be quite happy and declare that maybe that's the answer. If I end up with no, I need to make a way to choose it. So here is the exact formula for what to do in the case of a regular graph, a regular tree. So now I look at a graph, general graph, but converges to a regular tree. Now, if it's a regular tree, there is one big advantage in a regular tree over the general tree. In a regular tree, all the vertices look the same. Right? It's regular. So every vertex has exactly neighborhood D. So these H's are supposed to be exactly the same everywhere because there is no distinction. So I'm supposed to find an entrance law, this unknown H, is supposed to be the probability sequence of probability measures on X, right? So just X is my, either it's 2 or Q or 2 here again. And then I claim that there is going to be a fixed point equation, and I wrote you exactly what the fixed point equation is going to be in terms of, so the fixed point equation is you write BP of H equal to H, right? So if you write this operation, given the psi and the psi bar, this is just a normalization to make the sum equal to 1. Right? So this quantity is just a sum over X of all of this. So this is an operation over H of Y. It's a function, you don't know. And the operation now should make it equal to H of X and solve it. Not every H will be a solution to this equation. And then, once you found a particular fixed point equation, here is a beta functional, which is supposed to be the prediction for this quantity phi. Here is an explicit formula. It just involves various formulas for H. After you found an H, you plug it in. And what will be the prediction, the beta prediction? It says the following. You take only fixed point, first of all, right? H star, take only fixed point of this mapping. And among all the fixed point, takes the one for which this quantity is maximal. That's my prediction. Okay? Now let me explain to you on the board the source of this prediction. Okay, so I will need to explain to you 2 things here. Right? I will not explain why to take the maximum because it's a black magic. I don't know how to say why to take the maximum. Just take the maximum. But I can explain where this comes from and where this comes from. Now the principle why to take the maximum I can explain, but the explanation will be kind of fluffy. Here is the explanation. Look at this formula, right? You are doing some sum over various places. Now pretend that a part of the graph should go with one H, and another part of the graph should go with another H. So the exponential growth of the number of things you come from that part will be e to the size times this quantity in the exponent. And the other part will give you another exponent. Now you should go with the largest exponent because if, for example, you were summing them up, the largest will dominate. That's why you take the super node A. But this is very far from mathematical reasoning. This way can give you more clear mathematical reasoning that will also show you. Okay, so let me erase this. And I'll explain to you the consistency conditions. So first I'll do the consistency conditions. This is easy. So here is what we do. So now I do explaining on the beta energy. The explanation is special to TD, but it's kind of relatively general thing will follow the general. So to an extent, it's not very difficult. Just a formula will become very complicated. Let's take the form. Okay, so here is my point X, and here is my point B, and this point wants to send a message H. Okay, it has three children, Y1, Y2, Y3. Imagine X, this is actually the value, it's actually the value that I will have here, so I have an H here, and H here, and an H here. So I expect this H of X, what is sent here, like I explained to you before, there is only one sidebar of X, right, at this point. It's the local factor. And then I'm supposed to sum over y1 up to yb minus 1. Take the product from y equals 1 to b minus 1. The side of X. This is exactly what happens here. This is exactly the edges. This is what sits on these edges. There are three of them. This guy is what sits here, the local factor, and this HYI is what enters. Principle, this is what enters. And you can see that it has a big piece of an infinite tree. And because the tree is regular, what I see in every place here is exactly what I'm supposed to see here sent to this guy. And I can continue it forever, so it must be a fixed point of these equations, which is what I just wrote to you. Now, the only difference between these equations and what is written here, that here I was clever, and I recognize that in this particular case, because all the h's are the same, this sum I can write it also, so I can just write it also, and there is a normalizing constant, the sums. And what I can do here, I can write the sum and the product as a product from I equal 1 to b minus 1, the sum of my I, side x y I, h x y I. And because I have the same h, it's exactly the same expression, I can just write one of them and raise it to the power b minus 1, which is what they did. If the tree is random, then I have more difficulties because there may be H1, H2, and H3, which are different. The number here may be random also. And I need to write a similar equation but involving random variables. And an equation involving random variables is more difficult because it's going to be essentially an equation in functional equation, because it will say that the law of a certain variable equal to a law of some other variables. Here, it's much better because it's just a non-linear equation. In particular, if you take a case like easing or hardcore, H is just a weekly measure over two symbols. So the sum is 1. So it's really just one number between 0 and 1. So you have here a non-linear equation in one number between 0 and 1. But if you're lucky, how many solutions it will have? 2, 3, maybe lucky the only one. That's it. Now, how do you get this beta functional? That's the second part. Let me explain. If you saw, the beta functional was written as a difference between a vertex term and an edge term. get the vertex term, it's kind of simple. What you do, you say, look, let me look at the contribution if I take my graph and I take, add or subtract from it a particular vertex. So here is a vertex X. It has D children, 4. What is going to be the effect? So C, not C, what do they call it? P. P, vertex H is the effect on P by adding or removing the vertex. What happens if you add or remove the vertex? Well, you get the function psi bar of this vertex, and you also get these psi's which are sitting here. You also get these psi's which are sitting here. But you also get the h's which are sitting here. To summarize this. You also need to get these messages. And exactly like the calculation I did for you up here, it simplifies because everything is regular, so it's exactly the same h is going to appear everywhere, and it's the same function psi everywhere, so I can take again, I make it here, I make it into something to the power of b. I need to sum over the second argument, multiply by that. Here I need to sum over the first argument because I'm after such a thing, so I'm also going to sum over this particular x, which I did not do here, because here I was looking for a particular fixed x, now I need to sum over x. And I'm not after the z, but I'm after the log. This is the effect on the log. Now what would you expect? If you just take n different vertices, what you will find is n times this quantity. I mean, and this will be the log of the ZA, and normalize by 1 over n, you will get this. So this is clear to explain this stuff. Now you might start to worry and wonder, why did I subtract something? Now notice that if I do this procedure n times, every edge was counted twice. First I counted it here, and then I went here, and I took exactly the 4 births, and I counted it twice. So all these factors, psi xy times h here and h here, well, each of them counted twice. Okay, so since they were counted twice, what am I going to do? I will just remove half of these terms. That's what I mean. There are in general ND such terms. Why do I get ND over 2? Because how many edges do I have? I have ND edges. I counted them twice. I need to subtract ND over 2 edges. I divide it by n, so I need to subtract an edge factor D over 2 times. So this is correcting for, if you want, for overcounting the edge terms. And you could have also derived it directly by using formulas for trees. The point is, if you try to do it directly on a tree, you have to be careful because a tree has many leaves. You don't want to count the leaves. You somehow want to take a big tree, but do the calculation only up there, where you have a long distance from the boundary. Because here we every guy always has degree D. The trees, there are at some point in a finite tree, there are at some point things with degree 1. You don't know. Okay.
I don't understand why psi xy and hy appear.
Why here?
Yes, and psi xy hy.
Because, okay, what is an edge contribution? What is an edge contribution? An edge contribution is not just, here is an edge. The edge has a psi, but it also has messages coming from these two sides, right? One edge and another edge. It's really an edge in an infinite tree. Imagine looking at an infinite tree and taking out this edge or adding this edge. What will be the effect on this quantity? The effect on this quantity will be the factor psi of xy. And whatever the tree here tells you about the distribution of this guy y, and whatever this tree tells you about the distribution of this guy x, you sum over all x and y. That is a factor. That is a factor. But since in principle I should raise this factor to the power of the number of edges, and b, take a log and divide by n, which is this procedure that I just did. And took half, because half I want and half I don't. Really, there is a log here, but in principle it's a product of n such things, And then, observing the product of such things, this guy, the product of these things was counted twice each, so you divide by nd over 2 product of such things. And this will also work in principle, I mean, if it is correct. But this prediction works for a general limit, except that it will not be so simple because, as I mentioned, these d's are not going to be big, they're going to be random. These h are not going to be constant, they might depend on where you are in this random tree. What's the number of children you have and your children have? You know, you need to look at your whole family history all the way to infinity to figure out what is the h. Here it's much simpler, which is why we want to work on a irregular. Okay, so what we'll do in the second part, I will derive for you in principle this prediction, but for specific models. And that's also what I'll do on the slides. So hereafter, all my situation is irregular, and I'm trying to justify this prediction, or not justify this prediction. Sometimes I will get to predict results that say this is not. I'm trying to understand when and when is not this true or not. In the context of the 3 models I gave you, not more than that. That's already some open problems. You don't need to go far. Okay. So, what is the method in which we are going to try to prove this result? So, we want to prove this. The phi is equal to the prediction, and I'm going to do it specifically for the ferromagnetic easy model, for which it is actually true. For it. I'm not going to prove the theory which I know before. But the ferromagnetic easy models, and I claim that any level of interaction, every temperature if you want, even up to infinity, as long as the magnetic field is strictly positive, if a graph converges to a tree, I don't care what the sequence of graph is, converges to a tree, the formula for this factor phi is equal to the formula phi beta, and I tell you what to put in. What you should put in is what is called H plus. What is H plus? Take the fixed point equation of the beta, but the one with the largest value for plus. There are more than one fixed point. There are actually going to be 3 fixed points, sometimes, or 1 some other times. If there are 3 of them, no problem, take the largest of them. That's a plus. It's what is called plus 3 minus. Take plus, which is the largest. Okay, now how am I going to prove it? Okay, so here is the outline of the proof. And the outline of the proof is as follows. First of all, in principle, what you really should care about, you should know that I cheated you already, what you should really care about is not to take B positive, but you want to take B equal to 0. In easing, all the excitement part happens when B is equal to 0. I mentioned this to you maybe, and I plan to do it last lecture, but I will probably do it at some point later on, maybe the next lecture, not the next, I meant the last lecture. So if this is a phase diagram of easing, this is B, and this is beta, then there is a beta critical. Nothing exciting is happening for easing, except here. Ferromagnetic. Lots of exciting here things happen here. I'm not going to go over this. Ferromagnetic. So beta is always no negative. If it is small enough, nothing if here, right, beta equals 0, you have a product measure. Beta equals 0, there is no factor here, and you just have a product measure. So nothing really exciting happens for a product measure, and nothing exciting happens for a while, in the sense that there is only one possible limit measure. In many things, in many senses, the easing measure looks like a product measure. It has a small range correlation. If you change some value far away in the graph, it's not going to affect everybody else. Now, the place beta critical depends on your graph. It's different maybe in Z2, different in Z3, different on a tree. It depends, even on a tree or even on a regular tree, it will be a function of D. Different D will be different. But you can calculate. Now, what happens here, when B is positive, somehow the plus wins. When B is negative, the minus wins. Right? If you take, for example, imagine going up to B equal infinity. If you go up to B equal infinity, what happens? You give such a big factor to the pluses that you just choose to have all the pluses. If you give B equal minus infinity, you will choose all minuses. If on the other hand you will take beta equal infinity and B equal to 0, then because beta equal infinity, you really like to be all the same. You are very happy to be all the same. So what will you choose? You will choose either all of us plus or all of us minus. But because b is 0, we don't really know what to prefer, all of us plus or all of us minus. So we have a confusion. So there are two possibilities for the measure in this area. And that's why there may be a confusion. So the interesting part in easing is here. I don't know how to calculate it directly, but what I do know, and this is not difficult to check, is that the formula for phi, is going to be a nice continuous function in B. It may be not differentiable, but it's continuous. So if I can calculate the answer for phi everywhere, I can always take limits. That's what I do. So I declare this value as a limit when I come either from above or below. And as long as I don't calculate the derivative, it's fine, it's the same thing. So I just want to fix B positive. Now, the advantage of fixing B positive is that now there is a difference between plus and minus. Before, at B equal to 0, you didn't know. Should I choose plus, should I choose minus? Now I know, I should choose plus.
In your statement, do you mean we can take B non-negative?
Yes. B non... Which statement?
In the first line, it says that
Positive.
B energy is given by that.
B positive. Beta non-negative. B positive.
But say you take B goes to 0 limit.
Right. So if you want to know, you want phi.
Yes.
So I can calculate phi everywhere above the line. I can also calculate phi everywhere below the line because it's exactly the same as the limit. What do I do on the line? On the line, I'm just going to take limit to move this formula.
So you mean that formula is for beta to B equal to 0?
That formula is not true for b equal to 0, but the limit of this formula will work for b. It's not the same to plug in h. There is h there. The point, the change is, do I put the b inside or no? It's a limit of a function. It's not the function, it's a limit. The formula is continuous. H plus is not. That's the point. You have a fixed point equation, but the fixed point solution jumps. So you want to keep the positive, but just send it, go with it, and go with the value of the function. Okay, so now that we settled how to choose this thing, how do I really prove this formula? I don't know how to do it directly, but what I do know, I can calculate derivative. Okay, so instead of calculating 1 over n the log, I'm doing something which is usually not done in mathematics. Usually mathematicians, if they need to do something about limits, they like to integrate, they don't like to differentiate. I like to differentiate, as opposed. So what I do, this really, I'm looking after this limit. This is a function of beta on b, and this is also a function of beta and b. Instead of calculating the limit of the functions, I'm going to calculate the limit of the derivatives and then integrate afterwards. That's the principle. I believe, hopefully, that I can calculate the value of this at particular points beta and b, which are simple. I already explained to you that I can calculate it here. Right? Easy to calculate here. And it's easy to calculate here. I don't need it really. And it's easy to calculate here. This is infinity. I don't have infinity on this board, but okay, imagine me. And it's really even also impossible to calculate here. So now, if I can calculate derivatives, give me any point, I will integrate from some place to this point. Give me this point, I will easily integrate from here, or integrate from here, or integrate from here. I'm really free to integrate from wherever I want. I just need to have control of it, to know the derivative, and to know the values in some places in the boundary. I could have even succeeded integrating just one direction. Here I have more choices. So even if you have a problem here, I can go from here. Only thing, you don't really want to have a place surrounded by a problem, because then I will not be able to penetrate. As long as I have a way to, I will get it. Okay, so I need just to calculate the derivative. And why do I do the derivative? The reason is as follows. If I calculate the formula for z, you can see it involves the whole graph. It's not local at all, and I don't see what's the connection to the tree. But let me try to calculate the derivative of log of z. So I'm going to write you the derivative of log of zn. So zn involves some parameter b. And and I'm going to do the easy. It's the same principle in general, but I will just do it directly for the easy. Okay, so if I do that, of course, derivative of the law, and I need to differentiate into Cn. Okay, the Zn is a sum over lots of things. I need to differentiate each of these things. So one of the Zn is going to be a sum over x. I use these two terms. And then I have these terms. And I need to differentiate these exponentials in b. I just wrote you right now Zn, I did not write the derivative. But you know, if you differentiate the exponent in b, what you get is this quantity. Okay, so good, so I just get this quantity. Now notice what is sitting here. What is sitting here is simply my easy measure. Nothing else. And in all of these cases I have exponential. And always exponential, so I always get the easy something equal to the easy measure. So what I get at the end is a sum xin. Now this notation is a complicated notation. This just means take xi and calculate its average according to the Gibbs measure that you don't really know. It's not a piece of cake, but let's just write it like that. If this is true, then if you take 1 over n log Cn, derivative with b, of course you get this expression divided by n, which I like to write differently as xin. Let me write it as e over in x. This is the average of my magnetization at the point in, which is chosen at random. And I take an extra average over the choice of in. That's the same as taking, it's a very complicated way to write just 1 over n the sum of this. Now, why do I like this expression? Because I know that the law of whatever, I know that the law of Ball, B-I-N-T, should converge. This should converge for fixed t, especially t equal 1, it should converge to a 3. Okay, so I would expect that maybe this will go, as n goes to infinity, to the expectation, no, this is expectation, really, to the law of x in the center of some 3. This is the root of some 3. And this is an easy measure on a 3. But the problem is this is an infinite 3. I really cannot do an easy measure on an infinite 3, so I will take an easy measure on a finite 3 of size t. But then I still face a problem what boundary condition to put. So I need to choose, that's my h. And I'm going to choose h plus or plus. So this is exactly my prediction for the answer. And then if this is also a function of b, then I can integrate it like I explained, and I will get the value for the function. That's a principle. I will get convergence of the derivatives to expectations from 3 values. Once I do that, I will integrate back. The integration back is not very complicated. In a regular case, it's much more complicated in general, but it can be done. The difficult part is part of, you know, it's just the slide is very short. I didn't do much. I claim the problem is difficult, so something must be left somewhere. It is left here. And I will explain in the second part of the lecture on the board this type of derivation. Okay, so now converges to 3 values. So what do we need to do? Somehow you see what happens if you are on a graph. You can think about this way. What happens here? I can take a ball of size t. The ball looks like a tree. The problem is the rest of the graph does not look like a tree. But I can think of doing this calculation in 2 steps. First, I sum over all the values of all the vertices outside my ball. Use them as boundary values. Very complicated law, boundary. And then do this calculation on the finite tree that I have, which is rather large, with arbitrary boundary. Okay, so this picture is for a general case, but we are going to employ it only for the regular case. The point is, I have this easing model on this tree with some unknown boundary values. In principle, these boundary values come from averaging over the rest of the graph, but I don't know what they will be, so I'm preparing for the worst. I have some general boundary values, and I want to calculate the root minimum expectations. I want to calculate the value here of the origin as a function of z. If I can show it doesn't depend on z, I'm in business. I just take whatever it comes. I don't even care what the boundary is. Okay, so that's what I would like to do. I would like to prove that taking one z, taking another z, no matter what the z is, if t goes to infinity, I can make it go to 0. Now, in easy, there is going to be an order. It's an order. The largest value you get is putting the biggest boundary. What's the biggest boundary? All of them plus. Smallest value, smallest boundary, all of them minus. So the arrow will be bounded by difference between putting all plus, putting all minus, and calculating all the 3, and the limit equals to 0. T goes to 0. If this goes to 0, I'm in good shape. This is called the Gibbs uniqueness regime, and this is very easy. This will work for general model. Any model you will put, you don't need easy here. You can put any model, the scheme I just told you will work. So it just says that if beta is small enough, what I mentioned, if beta is small enough that there is no way to appear any really Gibbs measure other than 1, then you're in business, you don't care. You just put in principle, there was nothing, no need to do the soup. There was only one candidate, and then it will all work. This is easy. Unfortunately, this works only at the high temperature. This stops working once you cross this line, or once you cross some place. Okay? And I claim that things work everywhere in the easy. So I must be a little bit more clever and careful than this calculation. And now it becomes more easing specific. This principle applies always, but only gives you the high temperature result, which is not so interesting because all the combinatorial problems are in very low temperatures, are really 0 when beta is very large. And all the interesting physics is also low temperature. So from physicist's point of view, it's a non-interesting result. But in the easing case, we can do, okay, one more thing. Why do we have a problem here? We have a problem here, if you want, because while I told you that the function phi is continuous, I never said that the derivative is continuous. The derivative is actually discontinuous. That's the space there. If you come here or you come here, you get a different derivative. It's actually, you can see it because the function is the same here as here. So you have a function, so it's more like absolute value. The derivative, the only way it can be the same if it's 0. If it's not 0, it's not going to be the same. And exactly what it says. If you come from plus, you get the negative of coming from minus. Now, good for me, I only need to come from one side. That's why I broke the symmetry. Since I only need to come from this side, I will take the plus. But I need to prove it, right? And the way to prove it, okay, so on the tree, the counterpart on the tree is that if you take all pluses, you get a limit which is positive. You take all minus, you obviously get a limit which is negative because it's symmetric. This is b equal to 0, it's symmetric. But I claim that if I take only boundary conditions which are above 3 means that I don't have any boundary. It's like average. No, the maximum is put all of them to be plus, minimum is put all of them to be minus. I can do something in between. What is in between? Just to not do anything, or if you want to put random boundary condition. 3 is like putting nothing. Don't care about it. I claim that if I go anything between 3 and plus, I will still go to 0 at any temperature. And then I claim, this physically, not mathematically, since I put b to be positive, I have positive magnetic field, the rest of the tree outside this pole probably somehow should average slightly above 0 because of the magnetic field. Consequently, I must be only between plus and 3, and comparing between plus and minus was a gross error. I just took into account things which I should know. And indeed, we can prove, this is a proof of what I just told you, that plus will always be bigger than 3. I will explain this. There is no motoricity, so this will always be bigger than 0. But I can also compare it to 3 different between 2 values, and then if you sum up, you get this close to 0. This is easy specific, but the strategy extends to some models like POTS and hardcore. It does not extend to all models. It, for example, is completely useless for antiferromagnetic models. Somehow relies on the ordering, on the fact that everybody likes to be the same. If they would like to be plus, minus, then I get a headache. I don't know how to do that. Okay, so what do we do in the non-uniqueness regime? Okay, so easing, as I mentioned, already has a non-uniqueness, but as I will explain later on the board, the non-uniqueness can, the correct measure can be isolated by monotonicity condition. That's what I said. But I don't really need to go all the way from plus to minus, I just need to go from plus to 3. If you have Potts model already Q greater equal to 3, monotonicity considerations do not close the gap, and you need to do something. Again, as I mentioned, the physics predict that whenever you have error, so multiple things, you just take the largest one. And in a paper with Andrea Montanari, Alan Sly, and Naiki-san, we prove such predictions, but we prove such prediction in exactly one case. We just take the case of Potts models, any Q, Potts models, when it's believed to be true, and we solve it. So here is an example of a picture of what happens for Potts model. It's a Potts model of D equal to 4 and Q equal to 30. And then you have a piece in the middle where there is no uniqueness. Here, everywhere here, the 3 equal to the 1. In this piece, you have a non-uniqueness. Now, you can come from all places on the boundary. From the boundary, I can calculate everything. So I can come here, I can come there, I can come there. But then, if I have a point inside here, I don't know what to do. Okay, so I do know what to do, but I don't know a priori how to prove it. So if I do calculate this, so here is what's supposed to be the non-uniqueness regime and the formula. Right? So this is a formula I get by plugging the free boundary condition. This is a formula I get for the energy if I plug the one boundary condition. Here is again the same example of 4 and 30 with some magnetic field 0.05. So what am I supposed to find the answer? The answer should be the maximum. Should follow this up to here. It's a transition point. It's a critical beta. And then I should follow it. That's a physicist prediction. Now when I calculate the derivative, if I come from here with one derivative, if I come from here with one derivative, I will get a lower bound. I can come with one, I can come with the other, I will get a lower bound. I need to get an upper bound to prove that I should not stick with this or stick with that. So the answer, as I said, is the maximum of the two. And if I have time, I might explain at the end. I might explain how we prove this formula. It's not done by the technique of interpolation. It's very specific to Potts, and it's very complicated. I will explain how it's done. It's kind of a general principle that we know how to do it exactly in one case. So I can explain a general principle, but be aware that the inventor of this principle found only one example where they can apply this general principle. I don't know how general the principle is. The principle says if you can do blah, 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 everything will follow. Now the question is, can you do blah, blah, blah? Okay, so let me say some other models, as I mentioned. So the interpolation of parameters and some other means. The other means is what I mentioned. Other mean. You can get formulas for the TD regular tree because that has a very simple beta prediction. At least in the regular case, you know what you are facing. You count these fixed points. There are only finitely many of them. You can solve, in principle, this nonlinear equation, figure out from the beginning how many things you have to deal with. Where is the non-uniqueness regime, and so on. If you have equation in infinite dimensional space, who knows how many solutions they have and where they have more than one solution? I don't know. Now, examples. Now, the point here, the important point is there are examples of graphs that go to the deregular. What are examples? One example I already mentioned, uniformly random deregular graph. But here is another example, uniformly random bipartite deregular graph. What does this mean? This means I take the n vertices and I break them into two parts. Part 1, part 2. They all have degree D. However, the edges are only from vertices of type 1 to vertices of type 2. Now, the graphs are very different. Even the uniform graph over this group is much different than the uniform graph over all of them, because the general graph certainly does not break into two groups so nicely. However, as far as the local tree limit, it's the same, because you need to go and follow the whole thing to figure out that you really have a bipartite graph. You will not see it until you grow your ball with the size of the graph. Okay, so this is interesting and important. Why? Because of this step. Okay? There is a theorem proved by Sly and Son. They looked at the hardcore model and also the anti-ferromagnetic easing. These are very difficult models, much harder than easing reports, because those models have constraints in them. As you mentioned, in the hardcore model, you don't want to once. It's the constraints define one, you are not going to be one. And so anti-ferromagnetic is the same story. I am plus, you like to be minus. So it's very difficult to solve this problem. But it's very easy to solve this problem on a bipartite graph. Why? Because in a bipartite graph, naturally, the vertices split into group 1 and group 2. So we know what to do. We will put all the ones in group 1 and all the zeros in group 2. Or in the anti-ferromagnetic group, the plus in 1 and the minuses in 2. So you can prove that the beta prediction, which I mentioned, will hold in this two collection. Now, the beta prediction is becoming slightly more tricky. It's not exactly the prediction I gave you, because there is a periodicity here of size 2, also on the tree. You want to have occupied, not occupied, occupied, not occupied. And then it's different if you are part of the occupied group or part of the non-occupied. But if you jump by 2, it becomes exactly the same. Because if you jump by 2, you go for occupied. It's like a periodic thing. If you go on the period, you see the fixed point equation. So you have this, but the point is, if you take non-bipartite sequence, for example, the regular graph, it's actually known that the limit for large lambda in this case is strictly smaller. We can prove that. So, the beta prediction is no longer 2. In the sense, you have this group of bipartite, you have the group of the regular. They both converge to the same limit. The answer, not only it's not given by the formula, but it's not really the same. So actually, it matters what graph you take. So these are models where, because of the periodicity, something in the graph was important that was lost in the tree limit. So there was a global structure, this bipartite, that was lost in the limit. So this is like a warning for you that all these stories by physicists are correct most of the time, but here is a good example where they are totally equal. Now, of course, if you ask a physicist, you say that you were wrong, you're not listening to the story correctly, and you should have fixed it, right? By observing the obvious fact that since it's periodic, you should not do that, but do that. And with this approach, I can correct anything, right? And as I mentioned in this paper is all of the above. For people, if you take a Potts model, any beta and b, the beta prediction would hold on any sequence that converges to PD. It can be a deterministic sequence, bipartite or not bipartite. In the Potts model, since it's ferromagnetic, like in the easing, it's not getting to help you any periodicity. There is no conflicts here. We need it somehow to have the even, which is a technical problem, but this already shows you that our general scheme is not too general, because it doesn't even handle the odd case. So again, lower bound comes by interpolation, the scheme I explained to you, and the upper bound I will try to explain to you at least in one, it's come by what is called graph decimation, which is a different procedure. And these are the 4 references that I mentioned. And what I will continue in the second part, I will mostly talk about this paper, and I will show you how the interpolation done for the regular easing on a regular graph, which is the simplest. And then if I have time, I will tell you some of the things that we do in this paper as far as the graph decimation is concerned. Okay, so now we have a break, and I will continue in the rest of the lecture on the whole proving the actual derivation of what I mentioned here. This. So we want to prove the convergence of these derivatives, derivative of En, to this quantity. So I repeated here the formula for the derivative. Here the derivative of En with respect to V. It is average, which can be written in this way, where the average is the dimension. And we want to prove that we substitute the convergence of En to the limit. We will prove the convergence of the derivative to the formula for the derivative accordingly. Right? So instead, what we will do, we will not prove the convergence of the limit. We will do it at the end, but we will really prove that we want to prove the expectation x this is the expectation of the tree. There's actually no expectation. It's just a value of this measure for the easing measure is plus power. So then we will need to integrate and to somehow get it. When we integrate, we actually arrive to the beta to the energy. But let's leave this aside for now. Okay, so the main tool here, and this is also explaining many of the things I did already kind of on the slides, but never really explained, is the Griffiths inequality, which tells that there is a monotonicity effect with respect to boundary conditions of various values of, or with respect to parameters of various values of the easing. So let me state for you when I write Griffiths inequality. I will not prove it. There is a very nice proof in Bldg's book. It's very short and it's computational. So you're given, it's a very nice inequality. Given a finite set V and some collection of parameters J R. We have some collections of sets of V, and for each set there is a parameter, and all the parameters are greater than or equal to 0. That's important. And you consider the extended easing, which is given by, you take x, which belongs to minus 1 to the v, and you have a measure mu which depends on your parameter j, x, and there is a partition function which is j, and inside there is just the expectation sum, exponential sum I subset v. X R, where X R is an extension of the product of X and now, the easing corresponds to the special case where the JRs are all 0 except for two possibilities. One, when R is a singleton, it's equal to B. Two, when R is a pair, it's equal to either again 0 or beta, depending on whether the pair is in the set of edges or not. This is much more general because you can have a triplet, quadruplet, whatever you want, as long as all the parameters are non-negative. That's a ferromagnetic condition. So we have this condition, and then if you have this, let's call this. I'm just writing the equation numbers directly from DM10. This is DM10. If you want reference, or also for the rest of the proof, I can cite directly these equations. So there are two conclusions that we will use. One, for every A and B, two subsets of B. We have the property that uj xa is greater or equal to 0. This is just the average of xa, of this product, with respect to uj. So in particular, for example, this quantity is one such one. The average, this quantity is one such. So A is a singleton I, and it's the average on our graph of particular case. So it's always going to be greater or equal to 0 if all the parameters are 0, are non-negative. And the second condition, which is even more important for us, is the derivative with respect to JB. B is a subset, so JB is a particular one parameter of this object, uj xa, which is also, this is more difficult to check, the covariance under J xa xb is greater than equal to 0. So these values are actually positively correlated. Positive. J, remember, J is, there is different J for every index, so I'm differentiating with respect to this particular parameter. This is a function of all the J's, and if I do this with 1, I get a non-negative float. How are we going to use this result? So we are going to use this result again, notation numbers are coming from dn to 10. We take beta greater or equal to 0. I'm going to cite you the lemma b positive or greater or equal to 0. Actually, bi greater or equal to 0. G is b. A is the subset of b. Then I claim the following. Let me calculate what is x a g. This means you have a particular Ising measure, one of these things or three, whatever you want, any Ising measure you want, with this beta non-negative and all the bi are non-negative. They're possibly different. Sometimes I will need to put different b's, so that's why I'm extending to bi. This is a special case of this model, again, with one parameter beta for all the elements of E, for every pair, and the parameter bi for the element, single element B, and everybody else gets J equal to 0. If J is equal to 0, it's simply the same as not putting such products in the sum. Okay, then what is this quantity? This is just mu, of course, of x equal 1 minus mu x equal minus 1. This is exactly one of the quantities we might be interested in calculating here. And then and I will define xa plus and xa 0 mu. These correspond for easy mu. U is a subset of V, like in the picture I gave you in the slides. So you take some subset of V, you look at the edges inside, and what you put is 3 is 3 x equal to 0 and plus x equal to 1 and boundary condition. Meaning for U such that the distance U from U is 1. So everybody outside U, you either make it equal to 1 or you make it equal to 0. Those are the 3 and the plus boundary condition. And then I did not yet, I just put the definition. Now I finally write something in the lemma. So what the lemma says is follow. Take xa on U. It's going to be less equal to xa on the graph. And it's going to be less equal to xa on U is plus. This is exactly the slide I told you. You never need to look at boundary conditions that are not between 3 and plus. That's exactly the statement, but I have even more for you. This will go down in U, and this one will go up in U, and this is with respect to second U. So as you increase the set U, your lower bound go up, and your upper bound go down. If you can increase and increase and increase, you might actually hope that they will coincide. Which is exactly what I claimed. Okay, so let me prove to you this lemma, which shows you how you utilize the Griffith inequality. And once we do that, we are on our way. So now I'm going to write the proof. So I'm writing the proof of this lemma as it is done in this server paper, using this one as a black box, which you can read the proof of the black box in this video. Okay, so first of all, F1 to 14, which is this second condition, you get that the mapping from J to Uj XA is going up. With respect to partial order. I have here vector. No, I have a vectors here, so what does it mean going up? It means partial order. Partial order means all the coordinates are non-trivial. Maybe many of them are not changing, but whatever is changing in the right direction. And what you can see is that this just tells you that it's monotone in one coordinate, but if you have two vectors which are one above the other, you can just go change one, then change two, then change three, how many you need until you get there. And you keep increasing this quantity. Again, this notation is the same as this notation. Okay, now I need to, now let's see what is this guy, XAG, is mu J0 XA. Well, what is J0? We might specifically. J0 is going to be for singleton, it's going to be 9, and for pairs, it's going to be beta. And everybody else gets 0. That's my easy measure. Now I'm going to define some objects which are called J eta U R. Now J eta U R is J0 R, whatever R was. And then I add an eta if R has size 1. So it's a singleton, and is contained in the complement. So I'm not changing any magnetic field except outside. That's involved. I just put magnetic field eta to everybody outside U, and I put the usual thing everywhere else. Maybe adding. Now, obviously, this is going up in eta. You can see, right? You change eta. Making some people up, and so eta, so conclusion, eta going to XA to, let me write it this way, to mu J eta U XA goes up, and I also claim what is mu J eta U x is minus 1. This is very small whenever you are not on U. U is not on U. The reason is that all these people which are not in U, they all get extra magnetic field eta, which you should think about as very large. Which means that they have an extra factor. Where was my missing measure? Here. They have an extra factor e to the eta xu. If they're plus, they get e to the eta. If they're minus, they get e to the minus eta. The ratio is e to the minus 2 eta, and everything else is just a constant. It's not depending on it, bounded by something. So you can actually get it to be very small. And in particular, you conclude from this that mu J eta U converge to mu U plus when eta goes to infinity. which means what I wrote here. Check. This exactly gives you that. Because the guy XA, as we mentioned here before, because of the, this is increasing, right? We said this is increasing. So this guy here, this was going monotone. It is bigger than mu J O, XA, which corresponds to eta equals 0. And is smaller by what it gives you at infinity. So I just got you this part. How do I get the other bound? The other bound is even easier. Similarly, I will define now another object to compare. Similarly, let me define JRU to be JR0, but only if R is inside U. This is, of course, less equal to JR0, because either it's the same or we just pushed it to be 0. Consequently, and mu JRU is exactly what I defined as average with respect to free. It really, what I'm doing, I'm removing all the weights which are not inside U, so I get exactly the Gibbs measure, and Gibbs measure on U, ignoring the effect of everybody else. Everybody else is just ignored. It's not part of my Okay, so I get this part. Now, how do you get these things? You get these monotonicity properties by simply comparing these two guys. What is the effect of changing the U? In this case, when you increase the U, you put more indicators, you make it bigger. So it will go up. In the other case, when you increase the U, you reduce this set. The U is not appearing here. It's appearing on this thing. You're actually taking it to infinity. As you increase the U, you shrink the U complement, you make it smaller. You make it smaller, it goes down. Okay. Any questions about this book? Now we want to use it to our advantage by taking specific functionals, specific choice of this XA, and specific choices for something else, and then we will get control on the derivatives. At least we will get it to the statement that I mentioned to you, that we only need to control the difference between the class and the derivative. Okay, so now we know. Okay, so now using, so let me say that. Okay, so I have the derivative with respect to b, and is an expectation under n. This is all that I'm interested in. And let me write, I claim that using lemma 2, well, to start. I should call it constant. I don't remember seeing any problem. Two stars is between EA G0 G plus now I need to define what is the F's. So the F tilde 0 plus is equal to the value of x O in the plus on the ball functions xi on the ball So what did I do? I used, remember, what I need is the choice of I is done separately. I do average over I, but once I fix the I, what I'm supposed to do is to calculate xi, the magnetization at point I in the graph Gn. Okay, so I'm using this, and I'm comparing this magnetization over the graph Gn, taking for U the ball of size t around I, and choosing either plus or free boundary conditions. So that's what I wrote here. Now, this is true for any t, which is less than f1. This is true for any t, which is less than f1. But I'm going to fix the t and send the n to infinity. Now, if I send the n to infinity, what I have here is a local weak convergence for n. So now, local weak convergence. What I have here is a bounded function between -1 and 1 of the value of the ball, where I choose the center of the ball randomly. Local weak convergence should tell me that this should converge to exactly where the ball will go to, which is going to be what I will get. I will get from this that if I take now Gn converge weakly TD, actually I can get it for more general, but just converge weakly to T, then the En f tilde plus minus my bound, the bubble of plus and free. I'm writing it like that because I kind of, both of them, I just replace two is a plus or free, whatever one you want. It's two different functionals. This should converge, if n goes to infinity, does converge, the E will disappear. I will get here f tilde. Let me keep here B. Just f tilde. So you take exactly the same function, in this case a magnetization average on the center with plus or free boundary condition of a ball. The ball will now be inside my tree. In general, I should take an expectation over the law of the tree. In this case, there is no expectation because there is a single regular tree. Now, T is completely arbitrary, right? So let's say what we have. We have the limit in as n goes to infinity, the derivative of n. This equal to the limit so n goes to infinity, the derivative of n. This is less equal to essentially f plus tilde t. And this is equal to f tilde t. These are my bounds. Now I can take t to infinity. Right? T is arbitrary here. And I know that taking t to infinity will improve because this guy will go down and this guy will go up. So I can actually stick here the limit. As t goes to infinity. And a limit as t goes to infinity. So now you can see that if I can manage to make them the same, I'm done. So they said that I only need to control the magnetization between free and plus. I just proved it up to now.
Excuse me, what was the expectation with respect to the irregular tree?
Sorry?
You wrote expected value with subscript PD.
This is not really, okay. This is I just wrote because in general you might have a random tree, but if in TD this is the general, it will disappear. Otherwise I can keep it here. In principle, I should go over the law of the tree that sits here. For example, if I want to do the same for the Shreni, I can do exactly the same for the whole calculation will be the same because Griffith inequality doesn't care. Local reconversion doesn't care. There will be one difference. The tree here will not be the TD, but it will be this Galton-Watson tree, and I need to take the average over the piece of the tree that I'm seeing because it's a random. In the regular case, my life is much better because I don't need to do that. Which is why the whole thing is getting simpler. Okay, so now, yes?
Sorry. I was not in your first lecture, I'm sorry. So your local weak convergence is, I mean, you need a certain topology to formulate local weak convergence, I guess.
My local weak convergence says that if this is there is a finite space, okay. Yes, I need a certain topology on the set of infinite trees, and the topology is essentially the one of convergences of finite trees. Right? So I have every finite graph should converge to a finite tree eventually. And you can make it into a metric topology and so on. This is a very different thing in our finite. And of course I'm using one more thing. I have convergence theory of probabilities. I'm using the fact that this function is bounded. You can do, and actually this, I was cheating a little bit in the sense that in this dm10, we are not going through the derivative with b. That's why I have here 2 stars. There is also a derivative you can do with beta, and then you will get the correlation instead of the normalization. You will get 2 of them, but then you have the sum. And in principle, it's a non-bounded functional. It's a bounded function for regular tree, but it may be non-bounded if the degree is unbounded, but it's a function which has a uniform integrability. Hence, you can do that. That's why we want to do it. If you wanted just to do this case, you don't even need the uniform integrability. Okay, so we also know that these limits exist, because we know that this goes down and this goes up, which is why I didn't bother to write limits. And now we need to show that they are the same. Okay, so now there are 2 yeah, I utilize the whole business with Griffith inequality, so I will erase this word. So let's see what we need still to do. What we still need to do is to, okay, so let's start what we need. So we complete on so A and B. I want to prove that the limit goes to infinity of mu tilde T infinity. There is no mu. In my notes is for more general. Okay, so the people who will take the notes, if they copy my notes, they will do you the derivation for the general one. But I decided to be simpler here, so I keep forgetting to erase certain letters from there. So you have to see and this is equal to the derivative of B and equal to the and we know what these are. This is just the value of x plus 3, and this is equal to x. And here it is important that we take B positive, right? B was not positive, there is no hope for this, because if B, for example, is 0, this stays 0. There is a symbol, this stays 0, then this is not going to stay 0. But once B is positive, they become the same, hopefully. And B, and by the way, that's exactly what, everything here you could do also for the POTS model. Everything, all the models, everything, except the last piece will not work. This and this might not be the set elements. That's a level of uniqueness which I mentioned in this triangle. In this triangle we check, there are actually two different fixed points, and I'm just not going to be. Okay. The second thing, of course, we want to prove is that Pn goes to plus at the boundary. Theta equals 0, be positive, and this not yet not what I want to do this way. I want to do it at theta equals 0. Actually, I want to have b equal to infinity and I will go down from infinity. In the notes, the people who will be nice enough to take my notes and copy them. In DM10, we take derivative is beta of En and integrate from beta equals 0 to positive and from beta equals infinity. Other two, I had this diagram, I had three lines, three border lines. Here we go from above on this, here we go from above on the vertical lines, and here we go on horizontal lines from the side. In the paper DM13, DMS13 is my Pisan. We take the most general example, and we take the general model, and we decide that we don't know what people will need, so we integrate for whatever you want, and we differentiate both of them, just to make your life more miserable, more derivatives, more calculation, more fun. This is an elementary calculation in this case, as I mentioned. Elementary computation, even not in a regular case, because I explained to you in words what happened when you have B infinity, what happened if you are forced to put all pluses. Okay, you can calculate what happened when you put all pluses. It's not very good. And for part A, okay, so how do we do part A? So we already utilized the local wing convergence. We already went, now we are now in the world of trees. Right? We utilize the local wing convergence. We utilize the interpolation in the parameters. We utilize the monotonicity. We are still left with doing something on the trees. And as I mentioned, this is exactly the most fragile point of the whole argument, because this doesn't even extend now to pods. Everything else was working, at least for models which have some order. So, what do we want to do? Okay, so we really want to prove, so we already know, remember, we already know, let me call, okay, so we already know that if we take x norm plus t minus x norm this will be no negative, because we already know that the plus dominated. Now what we want, we also know that this will go down in t, because this guy goes down and this guy goes up. What we don't know is whether it goes down to 0. So the claim is that this goes down to 0. The claim is this goes down to 0. Now, in the case of regular trees, you can actually do the calculation by hand. You can write an iteration, and you can actually write a formula for this, or at least the function of t and this one, and you can try and show that it's actually contracting, it's kind of whoop, goes down to 0. In general, it's difficult to do that, but you can do it more for general things. What you can do, you can write, you want to prove, let me call this quantity A T plus, let me call this quantity A 0. So you want to write that A plus T minus A 0 T is less equal to a constant times A 0 minus A 0 T minus 1. Some universal constant. In general, the maximum degree or something about the graph. Now let's suppose you manage to do that. If you manage to do that, I'm going to simply sum it up. I'm going to sum it up, so I'm going to sum from t equal 1 to n. And what I will get is the sum from t equal 1 to n of these arrows here, and here I have a telescopic sum. So what I will get a0 of n minus a0 of 0, which anyway is at most 2. So these quantities are at most 1. So now what I have a decreasing sequence, right? A decreasing sequence whose sum from 0 to infinity is bounded. But there is no other way for it than to go to 0. So done. This is the decreasing sequence. It doesn't even matter the decreasing sequence, just sum of them. Sum sequence is tail is elements going to sum of the sequence, no negative. It's not sum of the cancellation. Every term needs no negative. Now, of course, I was hiding from you the most important fact, which is how I get this. Okay, so I'm going to skip this, of course. Only 5 minutes, and I'm going to say a little bit more, just to say that this comes from using I don't even remember what's the word for G. Griffiths is a G. Sherman is Hunt. Griffith Sherman. GHS inequality. And what the GHS inequality tells you is that local magnetization is concave. It's concavity. Local magnetization. This is quantities of this type with respect to the external changes. Anyway. If you remember, the Griffith inequality told us that there is monotonicity. Now you take a second derivative, there is concavity. Difference is that to get, you can get something like, I don't know, the Griffith inequality, monotonicity also for folks, but you cannot get, it's much more harder to get the concavity, and it's just not true. Beyond this thing, it's more, it's not true. It's much more specialized inequality. And using this concavity allows you to control one difference by another difference. So you're not just trying to control this, but you're trying to control a difference. Okay, that's as far as the story of the easing is concerned. Now I want to say a few more words about what is done in this other paper I mentioned with Andrea and Nike, which is dealing with the concept other models and Einstein, also still under the regular case. So we are now leaving the easing models. We've done the model with the key part, which is not even, I don't think this is even written in DM. I think even in DM, in the survey paper, we decided to skip it. You actually need to go to our papers. Okay, otherwise it's quite racist. It's not as elegant as what I thought. I don't know if you call this elegant, but it's less elegant. So what we prove in DNS is in this paper with other slide Nike, we prove one general result, which is all models. Something that physicists claim is always true, but we can prove it only in the regular case. So taking CM this is configurational model on random regular graphs. Configuration model in general, when you have a graph, there is still the restriction put on the graph that you will have no multiple edges and that there will be no self-loops. With an IHA, there is exactly one edge. In configuration model, you decide to even relax it. So, okay, I have D here, D there, and I just match all DN. I don't care where they come and where they go. So it's a much more simpler model. So on this configuration model, on random graph, which the message mentioned is really uniform, perfect matching of DN and half edges. You just completely forget where the half edges came from, and you just try to match them into edges, which makes for an even simpler model. So if you take this uniform model, if you call P the lim suit, and then goes to infinity 1 over n log n, this is going to be, of course, less equal. Let me put here expectation, it doesn't really matter. By Jensen, to put the expectation inside, this will be, of course, the expectation here is over the graph. Expectation over C, over the graph. So this is the expectation over CM, which is equal to the P. And this is true for any side. For any model, really taking the Bldg prediction is the same as putting the expectation inside the law. The expectation of the graphs. There is no expectation, there is not like it. This is already doing expectation over the measure. Now, in general, this might be strict inequality, but it tells you that the replica symmetric solution is always an upper bound. It's believed to be true in general. We don't know how to prove it in the non-regular case. It's an open problem. In the regular case, we can just do this calculation. It's very easy. Then we get this problem. In the non-regular case, it's not so easy to do the calculation. So conjecture, prove, honest. Sorry? Yes, what we don't know how to do. This is definition. This is trivial, and what we don't know, this is open. And this is also the only thing we actually prove. Everything else is just right. There is some small condition which is called permissible. Permissible is just to say that you don't want this psi to put too many things to be zero. You want to actually make sure, for example, you're not doing a lot of zeros. So you want to have some option of getting positive numbers. And as I said, the proof really uses the fact that there is a lot of randomness here to change this involves a lot of calculation with the sums. They just put the sum outside, do the expectation of the trees inside, and it becomes simple to do. Now, beware. So this is theorem 1 of this. Can I go over time by
Yeah, it's okay.
just 5 minutes, because I'm not going to go over there. I mean, not in these lectures. I'm not going to go over that. Corollary 1.9 says that there exist sides like that. For example, the hardcore case that I mentioned to you, with we know already that this, let's call this configuration. Could make it this phi configuration is smaller than phi, and that implies this actually implies that there exists a Gn in this ensemble G that converge such that the limit is what out. Not really concentrated in a sense. Right? I mean, okay, concentrated, but not, it concentrates on the average, but not, you can find the sequences, which actually will converge locally to a tree and will have a value bigger than your prediction. If your prediction is wrong, if your prediction is not the right value, then you can also find a sequence, a specific sequence, that will not work even the upper bound. But it works as an upper bound on the average. Most of them will be upper bound, but not all of them. The number of graphs is very large. That's the point. Right? So when I average here, well, many graphs were going out. And this is exactly what happened whenever you have the one RSP. Right? You have the RSP, the replica symmetry breaking. The prediction is actually not going to match this value. There is going to be a gap. And then there will be even sequences which have the same limit but have their own, even above value. Not only in the average, you have below value, and there will be sequences which will be above. That's exactly the example of the hardcore. The bipartite are giving a value bigger than this guy. They are the unusual on one way, but the random regular, which are the typical one, give a value which is strictly below. So your prediction is going to nowhere. It's not going to either way, in some sense. Okay, and then last thing is that, okay, then theorem 2. Theorem 2, this paper says that the T beta in the box is just for box. T beta is actually equals to P of H3 maximum H. And this is kind of the graph that I showed you, had only two possibilities. In principle, this is not a trivial theorem because there are more than 2 points. There are many. There are actually infinitely many fixed point solutions to the BP equation, but only 2 of them are global maximum. You just solve it. It's a regular problem. You just look at the function and it's different, many different local maxima, and prove that only 2 of them can be global maxima. Now, this is still not doing the work that I promised to do, and this I did not have time to do. But in principle, the interpolation, because there are 2 points, the interpolation will only give you a lower bound, you need to get an upper bound. And the upper bound, this is a main point of this paper, is an upper bound on phi by graph decimation. Now, what is graph decimation? It kind of, it's not doing any change in parameters. Instead, you go to what I said at the beginning, I wrote on the side of the board in the beginning, how to compare a graph of size n and a graph of size n minus 1. Well, the difference with them is one vertex. So I take out one vertex, maybe I choose a vertex at random, I take it out. I can calculate the difference between 1 over n log Zn and 1 over n minus 1 log Zn minus 1, hopefully. If I can prove that this difference is smaller than what I want, and I can keep doing it, then I have an upper bound. Now the problem is, how do I prove that the difference is smaller than phi? In the beginning it's not so difficult, but I need, as I decimate stuff, I get graphs which may be not random. I need to keep saying that the graphs still looks like 3, even though I took a lot of things, until I took almost everything. And keep bounding it somehow. Okay? So there is a scheme that we develop, how to do such tricks, and then we apply it on one particular case, as I said, and succeed. Because at the end of the day, the scheme involves an optimization problem that you need to prove is maximized over a certain pay point. And in the case of the regular inputs, we can actually do it. But in general, it can be quite difficult. And one more, the good news, the fourth lecture has nothing to do with the third.